So now we have Chinese remainder theorem. Even it has a very good application. Any model you do in mathematics has a very infinite number of applications in every technical domain. You need to explore it. What is Chinese remainder theorem? You consider AI, you consider BI, you consider MI or n set of positive integer. That's a better way I can write. To find unique x so that your x times, or I can say ai times x is congruent to bi times modulo mi. If you expand where I equal to 1 to n. If you run the value I from 1 to n, I am going to get simultaneous linear equation. This implies when you take I equal to 1, it is a1x is congruent to b1 modulo m1. When you take I equal to 2, it is a2x is congruent to b2 modulo m2. Again, etc. an x is congruent to bn modulo mn. What is your Chinese remainder says? For this family of linear equation, I will be finding unique value of x. We find unique value of x. My Chinese remainder says, when you have n set of linear equation, I need to find a common solution to that n set of linear equation, that is going to be x. Generally, the basic linear equation, Chinese remainder theorem, there will be a1 to an, all are going to be 1. So, standard form of the Chinese remainder theorem, standard form, always you consider the problem to standard form. If there is a ai, a1, get rid of a1, get rid of a2, get rid of an, make it standard. The standard form of Chinese remainder theorem is, don't consider ai, only consider x and bi. So I am going to get here, it is unique solution of the family. Unique solution of the family, x is congruent to bi mod mi. This is general Chinese remainder theorem. Every general Chinese remainder theorem will be converted to standard Chinese remainder theorem, where there should be no multiplier for the unknown. Get right. What do you mean by that? You find the inverse of ai, cancel off. a1 inverse, a2 inverse, a inverse under the class m1, m2, mn, what already we taught, and get rid of that and modify this expression. So it is going to be xi. This is the standard format. If you expand for different value of I, it is the simultaneous linear equation. Simultaneous linear congruent equation. Linear congruent equation. It will be x is congruent to b1 mod m1, x is congruent to b2 mod m2, etc. x is congruent to bn mod mn. This is my Chinese remainder theorem. What it says, for this n set of congruent linear equation, you will be finding the value of x, unique value of x, satisfying all these equations. Now what is the procedure? The procedure to go for Chinese remainder theorem is, first standardize the problem. What is standardize the problem? Nothing should be allowed as a multiplier of x. Get right by using inverse approach to get a standard form. Once you get the standard form, draw Step number 1. See, this is a procedure under Chinese remainder theorem. Draw M1, M2, etc. Mn. That is called modulo class. Then draw B1, B2, etc. Bn. That is called remainder value. This is called modulo value. Modulo value. This is going to be the remainder value. Now in the second step, this is called star means steps. Step 1. In the step 2, define capital M equal to product of small mi. That is M1 multiplied to Mn. M1 all modulo values will be multiplied to get capital M. Once you get the capital M, you generate capital Mi as capital M divided by small mi. That means we can write M1 equal to M divided by small m1. I can write M2 equal to capital M divided by small m2, go till end. The next step is find the inverse. Find the inverse of, very typical, be careful, inverse of mi under modulo small mi. People get confused, be careful. So find the inverse of capital Mi under modulo mi. Say it is going to be yi. That means what? This implies to find yi such that mi times yi is congruent to 1 modulo small mi. So I am going to get y1 etc. yn. I am going to get, because there are mi to mn. So for all m1 to mn, I am going to get y1 to yn. So then the last step is the solution component. It is going to be summation multiply small bi multiply small yi multiply capital Mi under modulo capital. This is going to be the solution under Chinese remainder theorem. The procedure is very simple. Standardize a problem. Generally, most of the problem will be standard. If it not standard, you standardize. What is standardize? In the left hand side, the unknown parameter should not have any factor. Get right using inverse approach, what already we taught. Once you standardize the problem, draw the modulo value, draw the remainder value, step number 1. Step number 2, get the capital M as a product of modulo value. Then using that product, you get the capital Mi till Mn by dividing capital M by small mi, M by M1, M by M2, M by M3, like this, go till Mn value. Step number 2. Step number 3, find the inverse of Mi under modulo small mi. Carefully, you may get confused with these two. Find the inverse of capital Mi under modulo mi, say yi. What do you mean by that? That is yi, you are finding the value of yi such that mi, yi congruent to 1 modulo small mi. It is small mi. Once you got the yi, once you got the mi, once you got the bi, I can do my solution. So you can write a table for that. So what are the 3 components we want? We want small bi, we want capital Mi, we want small yi, and we want capital M. You fill the value, it is given, it is, we can evaluate, it is inverse, you fill all the value, M is a product of, already you got the value, you just write the product here and multiply plus multiply plus multiply under modulo M, you are going to get the solution. I will go with one problem under Chinese remainder theorem. X is congruent to 2 mod 3 x is congruent to 3 mod 5 and x is congruent to 2 mod 7. And what is a very important condition under Chinese remainder theorem? So your small mi comma small mj, the GCD should be always equal to 1 for I not equal to j. Please verify whether pairwise modulo class should be relatively prime. So we'll go with solution. Very simple, not at all difficult, but very excellent applications are there under Chinese remainder theorem. What is your problem? X is equal to 2 mod 3 and x is equal to, x is congruent to 3 mod 5, x is congruent to 2 mod 7. See the procedure, you follow the procedure, you can enjoy your Chinese remainder theorem. Step number 1, draw M1, M2, Mn and check Mi, comma Mj GCD. GCD of Mi, comma Mj should be always equal to 1, pairwise they are relatively prime. Consider M1. Step number 1, what is M1? 3. What is M2? 5. What is M3? It is going to be 7. What is 3 comma 5? Relatively prime. What is 5 comma 7? Relative prime. 3 comma 7? Relative prime. Clearly, Mi comma Mj GCD is 1, the relatively prime for I not equal to j. For I not equal to j. In the same step, draw the B1, B2, etc. That is called remainder. These are all remainder value. What is remainder? I can consider B1 equal to 2, B2 equal to 3 and B3 equal to 2. This is step number 1. So it is an algorithm. Once you understand the algorithm, nothing you can find difficulty. What is step number 2? In the step number 2, generate capital M. What is capital M? It is a product of Mi. You multiply all small m values. That is, I can write here 2 or 3 multiply to 5 multiply to 7. The answer for that will be 105. This is step number 2. What is in the same step? Evaluate capital Mi. Capital Mi is capital M divided by small mi. This implies capital M1 is M divided by small m1. M divided by small m1 is going to be 35. Capital M2 is capital M divided by small m2, which is going to be 21, and capital M3 is M divided by small m3, which is going to be 15. So I got the step number 1, I got the step number 2, and the step number 3 is a typical. Be careful. I want to find, let yi be inverse of capital Mi under modulo small mi. This is a general statement. Now consider y1 is 35 inverse under modulo 3, that is small m1. So this implies 35 multiplied to y1 should give 1 modulo 3. Simple mathematics. So what is y1? You follow the procedure what already I taught. Either you do by inspection or you do by GCD method or using Euclidean algorithm method. You can find y1 is going to be 2. That is 35 2s are, that answer when you divide by 3, remainder is 1. Similarly, what is y2? y2 equal to, it is 21 inverse under modulo 5. This implies I should find 21 y2 is congruent to 1 modulo 5. So by either by inspection, take y2 some number 1, 2 like this. So I should get the remainder when you divide. Either you do that or you follow linear congruent method using Euclidean extension Euclidean method. You can find your y2 is going to be 1. Similarly, what is y3? Your y3 can be taken as it is capital M3, yeah. M1, yeah, it is 15. 15 inverse under modulo 7. This implies 15 y3 is congruent to 1 modulo 7. By inspection, I can write y3 is equal to 1. Everything is ready now. Easily you can enjoy. Construct the table, you will get the solution. What is this? By the table, it is Bi. Here it is Mi. It is Yi. It is capital M. Make 3 partition because 3 equations are given. What is your By? Bi is 2, 3, 2. You can write here 2, 3, 2. What is Mi? Mi is 35, 21, 15. That is 35. Then we have 21. We have 15. What is Yi? 2, 1, 1. So I am going to get here 2, 1, 1. And what is capital M? Capital M is 105. What is the solution? Solution looks like this. Therefore, your x can be taken as summation of Bi, Mi, Yi under modulo capital M. That is, x is equal to multiply these three. 2 into 35 into 2. The answer is 140. Plus multiply these three. Simple mathematics 63. Multiply these three. Simple mathematics 13. Under modulo capital M 105. So x is equal to, when you add these three value, I am going to get the answer 233. It is going to be 233 mod 105. Carefully, this should not be greater than your modulo class. What is the value? 233. What is modulo value? 105. Immediately you consider 233 divided by 105. Simple mathematics using calculator. So we have 233 divided by 105 equal to 233 divided by 105 equal to, it is 2.219047619. Goodbye to these two. Just multiply, you will get the required. X is equal to, it is into 105. The answer is 23. Modulo 105. Here the major work is getting the inverse. See, when you are getting the inverse, either follow inspection or modeling or Euclidean, extended Euclidean algorithm. I told you very clearly. Either, see, in all the other cases, nothing difficulty. Only the difficulty is getting inverse. There are 3 approaches. One is by inspection. Already I taught 1 or 2 problems. Modeling, I shown you how to do modeling. Extended Euclidean algorithm. I showed you how X and Euclid algorithm, I can find the inverse. Using that, you find the inverse, enter into table, multiply row wise, multiply, add all these value under modulo 105. This value after multiplying and addition, the value should not cross 105. If it cross 105, divide the sum value with that m value, get rid of the integral part, only keep the decimal, push back 105 the divisor, multiplier, I am going to get the answer. I will do one more problem. Very easy. See, sometimes the problem will be given in statement form. I will write the statement problem, then I will convert to mathematical modeling, then I will show you how procedure can be enjoyed for Cauchy's remainder theorem, and we can see. Find the smallest positive integer. Find smallest positive integer. When divided by 5, 7, 8 leaves the remainder 3, 1 and 6. So this is statement problem. This statement problem can be converted to mathematical modeling. That model can be taken into Cauchy's remainder theorem. Solution. Let x be positive integer. Divisor 5, remainder 3. Therefore, x is congruent to 3 mod 5. This is divisor, this is a remainder. Again, x is congruent to 1 modulo 7. This is a divisor, this is a remainder. Again, we have x is congruent to 6 modulo 8. See, simultaneous equation. What is the approach? 3 linear congruent equation. Not necessarily 3, you can have 10, you can have 100, you can have 1000. When there is a family of linear congruent equation having a single unknown, it is Cauchy's remainder theorem. So once you have Cauchy's remainder, once you recognize the Cauchy's remainder theorem, follow the procedure. What is the procedure? Step 1, step 2, step 3? Automatically get the solution. What is step number 1? Get small m1. Small m1 is 5, small m2 is 7, small m3 equal to 8. 5, 7 relatively prime, 7, 8 relative prime, 5, 8 relative prime. That implies mi comma mj, that is GCD, is always equal to 1 for I not equal to j. That is, any pair you take out of these 3, they are going to be relatively prime. The GCD is 1. First condition to go for Cauchy's remainder theorem. Second one, draw the value. It is B1 equal to 3, called remainder. B2 equal to 1 and B3 equal to 6. Step number 1. What is step number 2? Step number 2, get the capital M. What is the capital M? It is product of Mi. That is, multiply each M1, all the M values to get, that is M1, M2, M3. If you multiply M1, M2, M3, it is going to be 280. In the same step, you consider M1, that is M divided by small m1, that is going to be 56, and capital M2, it is M divided by small m2, it is going to be 40, and capital M3, it is capital M divided by M3, that is equal to 35. This is step number 2. What is step number 3? very typical finding the inverse. Okay. Step number 3. yi be the inverse of capital Mi mod small mi. That is, y1 is inverse of capital M1, that is 56 under mod 5. This implies, I can write here, this implies 56 y1 is congruent to 1 modulo 5. Either apply by inspection or apply modeling or apply extended Euclidean algorithm, I can show that your y1 is equal to 1. Similarly, y2 is inverse of capital M2, that is 40 under mod 7. That implies 40 y2 is congruent to 1 modulo 7. This implies, again same process, either you follow inspection or modeling or extended Euclidean algorithm to get the value 3. Again y3 is inverse of capital M3, that is 35 under modulo it is 8. So that implies 35 y3 is congruent to 1 modulo 8. So either again any one of the method we can write y3 equal to 3. Now construct the table. What is the table here? Maybe you know it is going to be bi, it is going to be capital Mi, it is going to be small yi, it is going to be capital M. 3 equations are there. What is b1, b2, b3? 3, 1, 6. What is m1, m2, m3? Capital M1 56, 40, 35. What is y value? It is 1, 3, 3. What is capital M value? Capital M value is 280. Therefore, my x is summation of bracket bi, capital Mi, small yi under modulo capital M. Therefore, x is equal to 918. After doing, I am going to get 918 under modulo 280. You can see here 918, 280. So this value should not be bigger than 280. If it is a bigger, use calci, apply division logic. It is 918 divided by 280. I am going to get the answer, that is 918 divided by 280. The answer is 3.278571429. Goodbye to this, just multiply, you will get the answer. Answer is 78. X is congruent to 78 modulo 2. This is how Chinese remainder theorem you can enjoy. Okay.